the differential equations. And the differential equations are for continuity, linear momentum, angular momentum, and energy. Okay. Boundary conditions also been completed, and today we're going to start with stream function, paragraph 4.7. But before we do that, let's just go back to the Navier-Stokes equations and see what we really have and what really is the practical problem with those equations. Okay. Now, the Navier-Stokes equation, three components in a Cartesian coordinate system. Rho multiplied by gravity minus partial dp dx plus the viscosity multiplied by partial d2 u dx squared plus partial d2 u dy squared plus partial d2 u dz squared is equal to rho multiplied by du dt. And let's call that equation 1, and that is only the first component of the three of them. So there are three of them. They're on your textbook and we've derived them. And I'm not going to write all of them out now because it is not necessary. So we've got three equations that are known as the Navier-Stokes equations. And if we want to design stuff, for example, if we want to design an aeroplane or an aeroplane wing, these are the equations that we want to solve. So if you go to these equations and you look at them, then from a practical point of view, you can say, well, if we want to start simple, then we can at least say, well, let's assume a steady state flow. Okay. So steady state. So no changes as a function of time. So we can throw out that equation, that part of the equation. Now, if we now look at the Navier-Stokes equation, we see that the problem we have is that there are four unknowns. And the four unknowns are the three velocity components and the pressure P. Okay. But we only have three equations. Equations. So what is the solution? The solution is we also have to use the continuity equation also. So if we also use the continuity equation, then we've got four unknowns and four equations. And the continuity equation is partial d rho dt plus ddx of rho u plus ddy of rho v plus ddz of rho w, and that is equal to 0. We can throw out this term because we've said it's a steady state problem. If we didn't throw out the time, if we wanted to solve this equation as an unsteady one, then you will see that we've got five unknowns and now four equations. So that is a problem. Now, most probably if you can give the mathematics for us so that we can solve this equation or equations analytically, most probably you'll get the Nobel Prize for mathematics. It hasn't been done yet. We are all looking for that solution. It's not known yet. So you must now think of the people 50 years ago who would like to design aeroplanes, the problems they had because there were no computers. So they were faced with this dilemma. Okay. Four equations, four unknowns, and these are the four equations now that they had to solve. The next assumption or simplification that they could do is to say, well, let's not consider the problem as a three-dimensional problem, but let's consider it as a two-dimensional problem. So if we've got it as a two-dimensional problem, then this equation can disappear, those terms can disappear, and the result is the unknowns are the pressure, the two velocity components, pressure U and V. But now we have only two equations of the momentum equation because we can't use this equation, and the continuity equation. Okay. So again, we have two equations of linear momentum, which are the x equation and the y equation, that one and that one. So equation 1 and equation 2, and we've got the continuity equation as our third equation. Three equations, three unknowns. Okay, and no analytical solution. We are going to see later in the chapter that in some cases there are analytical solutions for a very few simple problems. But if you want to go and solve the flow field around an aeroplane wing, that analytical solution is not known yet. We're looking for it. So the people made a plan, and a very good plan. Okay. And the plan is the definition of the stream function. Okay, paragraph 4.7, stream function. And the stream function is defined as psi. Stream function psi. And this function, which is now a function of x and y, firstly, this function has to satisfy the continuity equation. Has to satisfy the continuity equation. That must be the first thing that it must be able to do. And then it must be able to use to solve the momentum equation. So if we now look at the two-dimensional case, so we make the assumption it is two-dimensional. And if we look at the continuity equation, this one here, and we say that rho is equal to a constant, then ddx of rho u plus ddy of rho v is equal to 0. Okay. But that is a constant, that density and that density is also a constant, so we can take them out. Okay. Take them out, and we divide by the density, and the result is that the continuity equation that we're going to use is the u dx plus dv dy must be equal to 0. Okay, let's call this equation 5. So we've made quite a lot of assumptions in the derivation of this equation. Just go back. Steady state, okay, steady state, two-dimensional, and density is constant. So that's the continuity equation. And now, what is being done is to define the stream function psi xy so that we put it in the continuity equation. Okay. So if we look at this term here, then u is equal to that term there. So u is equal to the partial derivative of the stream function in the x direction. And this v term, if we look at that one there, and that one there, V is equal to minus partial psi dy. Why those two? Well, people tried a long time and they found that these two work. So it was by trial and error. So it is sort of a mathematical trick for replacing the two variables u and v with one function now psi. And what we also do is we say, wait, let's look at the vorticity or the curl of the velocity vector v. Because the curl of the velocity vector v is equal to minus k grad square of psi, where the grad square of psi is equal to 2 psi dx square plus the 2 psi dy square. And this is now equation 5. What we now do is, you're going to take the curl of the momentum equation, and we make use of this equation 5, and we can then obtain a single equation for the momentum equation. Single equation for the momentum equation. This equation looks like this. Partial psi dy multiplied by ddx of the grad square of the stream function minus the psi dx dy of the stream's function psi, and that is equal to the kinematic viscosity multiplied by grad square multiplied by grad square multiplied by the stream function. That is equation 6. And in this equation, the viscosity is the kinematic viscosity is equal to the viscosity divided by the density.
The third column that you have there, the first equation, the textbook has it dou x, and then dou y in the first bracket.
Which equation is it?
Top one out, dou y in the first bracket.
This one.
And now to left.
This one?
Yeah, is that the dou x?
What does the textbook say it is equal to?
That's also switched around in the textbook.
Is it switched around?
Yeah.
I'm not sure what you mean.
Yeah, u equals dou v dou y.
Oh, okay. Sorry. You mean here?
Yeah.
Oh, sorry. Okay. Yeah. Okay. Yeah. Okay. Okay. So.
The first equation then. In the first bracket, dou v dou y.
Okay. Don't worry about the small minor mathematics now. Let's just look at the principle. Okay. You can go and do the mathematics at home. The principle is, ladies and gentlemen, the principle is We look at the Navier-Stokes equation and we cannot really solve them. Okay. So we make some assumptions in terms of making it steady state. The density is 0, so it's incompressible. We make it two-dimensional, and now we end up with a continuity equation and the momentum equation. Okay, so it looks a little bit more simpler. And then this thing is defined where u is equal to that and v is equal to that. So this is quite important. This you're going to use. Okay. Then some more mathematics, and the result is firstly that this stream function satisfied the continuity equation, but we've got an equation where we only need to solve the stream function as function of x and y. Okay. And it satisfies the momentum equation. So that is now our new momentum equation. Okay. Now in a sense it is a victory, and in part a defeat. Okay. It's a victory in the sense that we only need to solve the stream function. It's a defeat because we're now going to have fourth order derivatives, and we're going to need 4 boundary conditions to solve the problem with. Okay. Now again, this equation, we still don't have the analytical solution of it, unfortunately. So there's another Nobel Prize that can be won. So they made some more assumptions. They said, well, let's assume the flow is inviscid. So the viscosity is equal to 0. So this term disappears. And then we also say the flow is irrotational. If the flow is irrotational, then the curl of the velocity vector is equal to 0. And the result is that this equation now reduces to what is called the Laplace equation. Very simple Laplace equation. Very simple Laplace equation. Okay. Again, there's no analytical solution, general analytical solution for the Laplace equation. Another Nobel Prize. Okay. So what did the people do to solve practical problems with? Well, firstly, they used this stream function so that they can get a practical sense of what happens around a flow, around a body, in the sense that these streamlines, if c is a constant, then we call it a streamline. And what is a streamline? A streamline gives us an indication of what the flow will do around a body. Meantime, what does a streamline mean? Streamline means that, let's suppose we look at a body. And the body might be a cylinder, and we would like to look at the flow over this body. Okay. Now, if you would get onto one of the air particles flowing over this body, okay, then it would do something like this. Okay. If you would get onto that particle there. Okay. Once you finished your ride and you come back, you get onto the next one, then it would look something like that. So those are called the streamlines. Okay. The streamlines are where the stream function is a constant. So that stream function might, for example, be 3. It might have the value of 3, and that stream function might have the value of 6. Okay. So everywhere where the stream function is a constant, then that is a streamline. Okay. So you can think of yourself riding onto the air particles over the body. So that is a streamline. Okay. Now what is very important also is that from these streamlines, we can actually learn a lot. For example, the volume flow rate between, okay, let's call that stream function value 1 and that one stream function value 2. The volume flow rate would be equal to the difference between the two stream function values, C1 minus C2 minus C1. Okay, now C2 would be equal to 6, C1 would be equal to 3, so it would be equal to 3 cubic meters per second. And that would be per unit depth. So that would be if in the Z direction, the height is 1 meters. Right. Now the next thing that we can do is, we might be interested in the velocity at that point there. We would like to know what is the average velocity. Now if I can blow up those two streamlines and look at that velocity point, if we now go and construct a line which is perpendicular on those two streamlines, okay? If it's perpendicular, and let's suppose this distance is 5 millimeters or 5 meters or whatever. Let's say it's 5 meters. Obviously you wouldn't like your streamlines to be that far apart, but that is now just in terms of showing the principle to you. Okay. We would like to know the velocity at that point there. Okay. Then the volume flow rate would be equal to the velocity multiplied by the area. The volume flow rate we have now solved as 3 cubic meters per second is equal to the velocity at that point multiplied by the area through which it flows. And that area would be equal to 5 multiplied by 1 if it's 1 meters in the Z direction. Okay. So it means the velocity is equal to 3 divided by 5 meters per second at that point. Okay. And you can go and solve it wherever you want. So that is an easy, practical way of getting a good feeling of what happens with streamlines. Okay. Now, unfortunately, in this textbook, not a lot of information is given on the stream function. Those of you interested in aerodynamics, if you go and page through old aerodynamics textbooks, you would see that a lot of work has been done on stream functions. And there are what I would call sort of building blocks that can be used. Stream function, building blocks. Now the most simple building block is called a uniform flow field. A uniform flow field. And for this uniform flow field, there's an equation U is equal to that and V is equal to that. Now typically it's that. Okay. So that is the building block which is called a uniform flow field. If it flows in the other direction, then U is equal to minus U infinite. As easy as that. Okay. So that's the first type of flow field. The second type is what is called a source. A source is where the flow from a specific point flows in a radial direction like that. That has been called a source. And again, for the source, there can be written the U component and the V component. And the opposite to the source is called a sink. So the sink is the opposite. Everything flows into the hole, into that point. From everywhere from outside, it flows into that point there. And the third type, that is now a sink. Now the source and the sink is related. It's actually one type. It is just the signs, the pluses and the minuses that differs. And the third type is the vortex. The vortex looks like this. And again, for the vortex, the U component and the V component, you can go and get it in the textbooks. Now, by adding these different building blocks, we can generate different flow fields. By adding these different building blocks to each other, we can generate different flow fields. For example, we can generate a flow field that looks like this. Okay, the flow around the cylinder. That also does this. I specifically drew the cylinder first so that it's easy to identify. Now what building blocks would give us that flow field? The building blocks that would give us that flow field, I think, was a uniform flow field and a source and a sink next to each other. Source and a sink just next to each other. So that is what that flow field we generate. The other type of flow field looks like this. It forms an elliptical object. Something like this. Again, I draw the elliptical object first so that it's easy to identify. And then, here on the inside, looks like this. What would give that to us? It would be a uniform flow field plus a source plus a sink with a certain distance apart. So this is the source sitting here, looking like that. A uniform flow field, a certain distance away x, then there would be a sink. So those three building blocks would give us the flow around a body like that. Okay. So practical application would be, maybe you're interested in the flow field around the Zeppelin, and you've got it. Okay. And again, by adding the distance x or the strength of this velocity field, you can generate different bodies. You might also may be interested in looking at the flow over a new racing car. And maybe that might be the front part of the racing car. Then you can use this to determine all the velocity fields over the windshield. Another one which is very, very interesting is also generating a cylinder, but the flow field looking like this. Okay, if I remember correctly, it would be a uniform flow field plus a source plus a sink plus a vortex. Now the interesting feature of this velocity distribution, if you look carefully, my sketch obviously isn't that nice. You can go and draw it out exactly. But if you go and look at it very carefully, you will see that the distance of this streamline and the distance of that streamline are not the same, which means that the velocities are not equal. If the velocities are not equal, then it means that the pressures are different. And the result of this is that this one generates actually a lift force. A lift force. And aerodynamic profiles and aeroplanes like that has been developed with rotating cylinders. Aeroplanes with rotating cylinders generates lift. Okay. And then aerofoils. What people did is they would look at, let's call it the center line of an aerofoil, and they would go and put lots of vortexes over this of different strengths. Okay. And the result would be an aeroplane wing. An aeroplane wing. Now in the 1940s and the 1950s and the 1930s, people used this approach to design aeroplanes. So aeroplane wings was designed like that. Okay. One of the important things is if you want to do aerodynamics, you have to be very good in mathematics. The mathematics, not nice to handle, but in general, that is what they did. Now what was wonderful is that they could actually predict the lift, but unfortunately they couldn't determine the drag. Why not? Why wasn't it possible to determine the drag with this approach? Well, it lies in one of the assumptions that we made. In one of the assumptions we said it is in viscous flow, so the viscosity is equal to 0. Yep, all right. So the assumption was made that it is irrotational flow. The viscosity is equal to 0, and that is why it wasn't possible to determine the drag. Something else that wasn't possible was to determine the separation. Usually, depending on the profile shape, it was possible to get flow separation. Okay, so we couldn't predict drag and they couldn't predict flow separation. So together with this theoretical aerodynamics and wind tunnel work, many of the aerofoil shapes which are being used today have been developed. CFD really helped them to refine it, but most of the development work was done with this theory. So that's the background to it. Now something else that is important is that there are also what is called potential lines or potential functions. And these functions would be psi is equal to psi dx and v is equal to psi dy. Now what are they? They are just lines which are perpendicular on the streamlines. So if these are our streamlines, psi3, psi2, psi1, then these lines are just perpendicular on these lines. And sometimes it was easier to develop or to derive the flow fields using the potential lines than the streamlines. So it depended on the application.